This is a chip made by Taiwan Semiconductor Manufacturing Company, and we're here at its California offices for a rare interview about one of the next big bottlenecks in the race to make enough chips to power AI: advanced packaging.
We build the silicon, we get the HBM from the memory vendors, and then we build up the organic interposer in our packaging fab and do the pick and place.
But right now, TSMC sends almost every chip like this, even the ones made in the US, back to Taiwan for packaging. Because while you might think of microchips on the nanometer scale, this is what a modern high-performance chip looks like. A bunch of smaller chips, protected, tested, bonded together in the packaging step of chip making. And it's almost all happening right now in Asia. That's about to change. TSMC is breaking ground soon on 2 new advanced packaging plants near its new chip fabs in Arizona.
Packaging used to be an afterthought, right? Literally, you would put your junior engineers on it, but now, obviously we know it's as important as the die itself.
You simply can't ship a piece of silicon for a product without putting it in a package.
Now, Nvidia's reserved the majority of TSMC's leading CoWoS packaging technology, with TSMC reportedly outsourcing some packaging to third parties because capacity is so heavily booked.
It can emerge as a bottleneck very quickly if people are not making the CapEx investments proactively to account for the surge in fab output that's going to be coming in the next couple of years.
Intel is the other major player with its EMIB packaging technology, primarily happening in Vietnam and Malaysia. But the US-based chipmaker is doing some advanced packaging in the US now, in New Mexico and Arizona, where we got gowned up to see the clean room where it happens.
These are the chips or the dies. The green rectangle there is what is called substrate or the package.
We went to TSMC and Intel to find out what exactly advanced packaging is, why it matters, and what a constrained supply chain means for Nvidia's competitors and the ability to fill insatiable demand for AI chips. It's no secret that manufacturing the world's most advanced microchips is so expensive and complex that only 3 global companies run fabs at the leading edge: TSMC, Intel, and Samsung. Those same 3 are also the leaders in advanced packaging. Whether it's GPUs or CPUs from Nvidia, AMD, or Intel, custom ASICs by Amazon or Google, every chip must be assembled onto a system so it can interact with the world around it.
This will connect to a circuit board. And on a circuit board, you may have multiple of these parts. They become kind of a blade into a server rack.
Paul Rousseau has been at TSMC for 25 years and now heads up packaging solutions in North America. He likes to explain chip packaging by comparing it to packaging for soda.
If you think about Coca-Cola historically, the only way you could buy a Coke was at a soda fountain. Once the bottling technology came along, that revolutionized the distribution of Coca-Cola. And it evolved, right? We went from glass bottles to aluminum cans to plastic bottles, but the primary function was still the same. It was to protect and contain the product. And if you look back at our industry, it was exactly the same.
Indeed, inside a packaging lab, chips are coated with protective materials so they can be handled and installed, and they're put through rigorous environmental testing. But most importantly is the packaging portion to contain the chip and help it quickly and efficiently connect to a system. And as chips have gotten exponentially more complex in the age of AI, standard packaging has evolved into advanced.
Most mobile chips and analog chips are not chiplets, but they used to come with one wafer, and that comes out of the main chip factory. But now multiple chips are being manufactured with different technologies and sometimes even different places, and then they're pulled into one very large chip, and you need advanced packaging to do that, to have the interconnects. And up until about 5 or 6 years ago, nobody was doing this.
We're putting multiple pieces of silicon together inside the package and interconnecting them. It's really the natural extension of Moore's law into the third dimension.
Here's how it works. First, individual chips or dies are bumped. Micron-scale metallic bumps are added to the silicon surface as connection points for the electrical signals to travel through.
You can see the massive amounts of bumps. This is to connect to the outside world.
Then the dies are picked and placed, attached to the base layer of the package, the substrate that connects them to a larger system like a circuit board. The substrate is several layers of a resin-type material that routes signals and distributes power to the chip using copper. Companies like Intel are also investing in glass substrates because it enables better control and finer features for the growing systems needed for AI. Because as AI leaders like Nvidia progress their chip density and performance rapidly, their advanced packaging needs are evolving quickly too.
They want to put more and more GPUs, more and more high bandwidth memory into one package.
And so we have shortages because this AI demand was a little bit unexpected. So people had not put in enough capacity.
While packaging is a necessary step, the most advanced kind is what's in short supply. To understand why, let's break down the different types. Many chips, like CPUs, are mounted directly to the base substrate in what's known as 2D or flip chip packaging. But for more complex chips for AI, like GPUs, chip makers need 2.5D packaging, pioneered by TSMC in 2012 with what it calls CoWoS, chip on wafer on substrate, now used by customers like Nvidia, Google, Amazon, and MediaTek.
Chips are really side by side, so they're really 2D from that perspective, but we have a communication channel underneath, and that's the extra half dimension. That's what we call the interposer.
The interposer consists of additional layers with high-density wiring that acts as a bridge between multiple chips that sit on one substrate. This enables tight interconnections that are a game changer for mounting stacks of high-bandwidth memory directly around the chip.
You might have heard of people refer to the memory wall, right? You just can't get enough memory inside your compute chip to fully utilize it. So when we introduced CoWoS, we were able to bring the HBM memory right beside the compute in a very efficient way.
TSMC has moved through 3 different CoWoS generations, from CoWoS S
In the center, it's like one big piece of silicon, and there's 4 HBM around it.
to CoWoS R, now to CoWoS L.
You can see here 2 very large chunks of silicon in the middle, and then you have 12 HBM that surround it.
CoWoS L was first used in Nvidia Blackwell GPUs that started shipping out last year. And it's this CoWoS L capacity that has everyone worried, because Nvidia has reportedly reserved the majority of it.
We are seeing a lot of demand, and so we're trying to respond to that demand. Obviously, capacity has been tight. We're trying to solve that issue.
Do competitors to Nvidia need to worry that so much CoWoS is reserved for Nvidia?
I think we've always tried to be everyone's foundry, and we will keep trying to do that.
Of course, TSMC is not the only option. In 2017, Intel began its 2.5D packaging, called EMIB, Embedded Multi-Die Interconnect Bridge. Instead of an interposer, EMIB adds a silicon bridge within the substrate to allow the high bandwidth memory to communicate with the logic chip.
We're just embedding these really small pieces of silicon just where they're needed to make an interconnect between them to kind of connect them all up. So there's a cost advantage.
So instead of having a silicon interposer that covers basically all the chips that you're laying down, it would basically connect just the edges of these chips, right? So it's going to save time, it's going to save material, and it's going to allow you to work with smaller chipset sizes.
Samsung, which declined an interview for this story, calls its 2.5D packaging iCube. And all the players are also working on what comes next after 2.5D, 3D of course. Samsung calls its 3D X-Cube. Intel's is Foveros Direct. TSMC's is SOIC, System on Integrated Chips.
That becomes true 3D technology. So instead of having the chips side by side, now we put them one on top of the other. So the chips one on top of the other can really behave as if they're one chip.
Less space between chips means communication between them takes less power.
Our customers come and tell us that, the amount of silicon they can put into a data center is limited by the amount of power they have. And so if we can lower the power, then we can sell more silicon and the data center becomes more powerful.
TSMC says it'll be a couple years before we see products made on SOIC. Memory companies like Samsung, SK Hynix, and Micron already use 3D packaging to stack dies into high bandwidth memory inside advanced packaging fabs of their own. As they hustle to get HBM out the door fast enough, memory companies and TSMC and Intel are also looking to hybrid bonding to replace bumps with flat copper pads, boosting the number of chips that can fit in a stack.
Instead of a bump, we could do a pad-to-pad connection, which is almost no distance at all. And so that gives us a better power performance, and it also gives us better electrical performance since the shortest path is the best path.
From 2D to 3D, right now, the vast majority of advanced packaging happens in Asia.
And the challenge really becomes, primarily for the US, is national security, right? You have North Korea looking down at South Korea and all the challenges there. You have Chinese boats and airplanes deciding to blockade Taiwan on occasion.
And at the volume leader, TSMC, 100% of packaging happens in Taiwan. Even chips made in TSMC's new Arizona fab are sent to be packaged in Taiwan, where TSMC is ramping up 2 new packaging plants.
Historically, packaging migrated to Asia probably in the 1970s, right? And a lot of it had to do with cost and labor, because at that time, packaging was very manually intensive.
Now, much of the process is handled robotically, and there's a big push to reshore as many manufacturing steps as possible amid ongoing geopolitical tensions and supply chain concerns. So TSMC is about to build its first 2 US packaging facilities, eventually adding high-volume packaging capacity near its chips being made in Arizona, although it wouldn't share when construction will begin.
It's going to make it easier to get your turnaround time with the packaging rather than have to ship it back to Asia and bring it back.
Meanwhile, US-based Intel does the majority of final packaging assembly in China, Vietnam, and Malaysia. But it completes certain portions of EMIB and Foveros entirely in the US, in New Mexico, Oregon, and at this site in Chandler, Arizona, near Intel's new 18A fab that started volume production at the end of 2025. This is an Intel Xeon server chip, and we are inside Intel's advanced packaging lab, where what happens is they take chips like 18A from Fab 52, and they actually connect them to the systems that we as consumers see, like this, with tens of thousands of wires, each thinner than a human hair. Although Intel has yet to solidify a major external customer for its 18A fab, Gardner says Intel's had packaging customers since 2022, such as Amazon and Cisco. Now, Elon Musk has tapped Intel to package custom chips for SpaceX, XAI, and Tesla down the road. And Nvidia is looking to package at Intel too, as part of its $5 billion investment in the chipmaker last year.
I do think that the chip companies want to show the US administration that they will do business with Intel, and the lower risk path with Intel is to do packaging.
So could Intel find a major chip manufacturing customer through the back door of advanced packaging?
There's benefits of everything being in one place. And so yes, with some customers, that's kind of an inroad to that.
It's one thing to have the leading edge foundries with the tools and the engineers, but that's only as good as the packaging, in my opinion. So you're not outsourcing that or relying upon a third party that you have no control over for those capabilities.
Smaller third-party packagers, called OSATs, handle part of the process, like Amkor, a TSMC and Intel partner that's building a packaging site in Arizona. Almost all chips end up at an OSAT for the simpler steps, and now more of the advanced steps too, as TSMC struggles to keep up with unprecedented demand.
We're increasing our CoWoS capacity at 80% CAGR, our SOIC capacity at 100% CAGR. So our packaging numbers are growing very substantially.
The world's largest OSAT, ASE, sees advanced packaging sales doubling in 2026. It's building a huge new CoWoS site in Taiwan, where Nvidia's Jensen Huang attended the opening of another new packaging site by ASE subsidiary Spill last year. But as TSMC brings 2 advanced packaging plants to US soil, this lesser-known step in the chip-making process may eventually help the US regain some of its long-lost lead in silicon. Are we talking a long time? Are we talking 5 years, 10 years before we're going to see volume production for advanced packaging from TSMC in the US?
We haven't given a specific timeline, but we're trying to move as fast as we can to solve our customers' demands.